everybody. I'm Jennifer Westendorf. I am the director of the Musculoskeletal Research Training Program at Mayo Clinic. Last year, we were fortunate to be awarded a supplement to our T32 training grant from the NIH. And the supplement is meant to provide workshops on AI and machine learning to the musculoskeletal community. As you all know, and I'm sure you're aware, is that in the last few years, machine learning and artificial intelligence have matured sufficiently to be omnipresent in science, medicine, and really all aspects of society. So today we are pleased to provide an introduction to AI and machine learning for musculoskeletal applications. This will be the first of 4 workshops we will hold this spring. So we hope you come back to future workshops as well. Before we get started, I want to acknowledge 3 people who have been key to developing these workshops. Dr. Hilal Meredith Kramers provided the initial vision for the supplement and was instrumental in planning all of these workshops. Second, Dr. Alex Weston is a member of our planning committee. He will be facilitating today's discussion and will also be leading our second workshop, which will take place on March 4th. And finally, today's presenter is Dr. Poria Ruskov. Dr. Ruskov earned his medical and joint master's degrees in public health and health professionals education from Tehran University of Medical Sciences in 2018. Poria currently works as a postdoctoral research fellow in the Radiology Informatics Lab at Mayo Clinic under the mentorship of Dr. Brad Erickson. And he also works with the Orthopedic Surgery AI Laboratory, also called OSAIL. His research involves computer programming, medical and data science research, and the application of AI in medical imaging. And he's currently contributing to several AI projects. Some of them you'll see and hear about today. These projects are at the interface of radiology and orthopedics. So I want to thank you for coming today. I believe you will learn something from these workshops, whether you are an AI novice or an AI pro. I hope there's something here for everybody. So before we turn this over to Poria, I'd like to let Alex say a few words, and he'll provide guidance for today's discussion. Alex?
Yeah, so this, just a quick note. So yeah, this is going to be an interactive session. And so if you have any questions as Priya is presenting, 2 options. I would encourage you to type them in the chat, and then I'll keep a list of questions in the chat and ask them of Priya as they come up. And the other option is, if you really want to ask your question verbally, I would encourage you to use the raise your hand feature, which is under reactions in the bottom right of your screen. And that pops you up to the front of the queue just so that we can see you and I can call on you to ask a question that way. And I think Poria has planned breakout rooms and some interactive polls as well that will sort of facilitate the discussion as it happens. So with that, I'll hand it over to Poria.
Thank you, Alex, and thank you, Dr. Westendorf. Hello, everyone. Hope that you're doing great. This is certainly my pleasure to be with you today and hope that we can have a good discussion. I think that Dr. Westendorf and Alex already mentioned all the important points that we needed to start the workshop. So I'm just going to share my screen and jump to my slides. So I'm going to start with a quick introduction about these workshops and why we are running them. Dr. Westendorf already talked about the general vision. We are actually going through 4 different workshops coming up every 1 or 2 months. The first one is today, in which we talk about the general picture of machine learning. And after that, we are going to talk about tabular data and how to apply machine learning to that type of data. Then we talk about the medical imaging and finally about the medical text data. So the mission of these workshops is not to go through details and talk about how to do the programming with these type of machine learning techniques. We are just going to give you a kind of big picture of what is happening in that world. So we really want you to understand how people design machine learning projects, how to go through them, how to form teams, what stories happen behind the scenes when you see a machine learning paper coming up in a journal, and try to help you understand if you want to do something like that by yourself or maybe by some of your teams, what different steps you need to go through. But in case some of you are interested in doing some real coding things with machine learning, we do provide you with resources and further recommendations on where to start and how to proceed with that. So with that said, I would also like to mention that there are a few areas in machine learning that we are not going to cover in these 4 workshops. namely video analysis, audio analysis, genomic data analysis, drug design, robotics, and reinforcement learning. They all definitely are important areas of machine learning, but due to the limitation of time we have, we only decided to focus on the most applied areas of machine learning in medicine, which are definitely tabular data, medical imaging, and medical text, at least for now. So I'm going to jump through the current workshop and talk a little bit about what we need to talk about, which is actually the aims of our today's workshops. So we are going to talk about 4 main themes. First, to define AI, machine learning, and deep learning. Second, to introduce a high-level classification of machine learning algorithms. Third, to discuss the routine life cycle of a machine learning project. And finally, to discuss some of the key concepts, challenges, and resources that we usually work with or deal with in machine learning development. As Alex said, I'm going to keep this workshop as interactive as possible. We need to go through many slides together, but I would make sure to stop every few slides to make sure everybody is following. And if somebody has some burning questions to ask, we would be more than happy to answer. Now I would like to talk about something very introductory. So the charts that you're seeing here actually shows the number of publications in PubMed that have been related to machine learning or have used machine learning in their methodology. This is not a very new image. As you see, it actually had been published in the middle of the year 2020, but the photo is quite interesting. So I decided to keep it here for you and talk about a few things here for you. So the first thing that you definitely have mentioned so far is this, ascending kind of curve here that shows the number of publications with AI has actually increased in an exponential way. But the other thing that also is interesting, and it somehow surprised myself, is that if you look at the right side of your screen, you would see that, although we do see those areas that have been through AI and machine learning for long, like radiology and pathology, we do see other fields as well here that have been increasing in the number of publications they have with AI and ML. For example, look at the surgery here. So it seems that surgery even has got more publications than something like neurology or something like cardiology, which are pretty much famous for the application of machine learning they have here. And other disciplines are also following very fast. So it would not be too late that we see a lot of publications coming of machine learning out of these kind of areas. So one thing to have in mind is that it seems that our medical world is changing a little bit. I do disagree with that kind of a statement that machine learning or AI or anything related to computers is going to replace physicians or anything in the medical world, but it definitely is going to change something here, right? So basically, with the number of papers that you see is coming up and everybody talking about that, certainly many of you have gone through conferences talking about ML and AI, you have probably felt or sensed that urge to learn about AI and how to deal with that in the upcoming study. So this is something to have in mind as we go through these slides, that we are talking about something that is already a trend in many disciplines and will soon be a trend in some other disciplines as well. Now I would like to ask you some introductory questions. My first question is that, how do you define machine learning? And for that, I would like a couple of you to turn on your mic and try to define machine learning for others, whatever that comes to your mind, regardless of you have read that somewhere or it is something that you have created by yourself. Any volunteers? Someone? Alex, if there is no volunteer here, then I'm going to ask you.
So I usually say that a machine learning algorithm, the phrase I like to use is data-driven. Yeah. So rather than pre-programmed, it learns the relationship from the data.
Yeah, that's totally correct. And this is something that I would also like to mention here. So basically, whenever we talk about AI, machine learning, and deep learning, we think that we understand what these things are, but sometimes we need to step back a little bit and try to define them so that we understand exactly what algorithms are labeled with term AI, ML, or deep learning. Now, I would like to start with defining AI or artificial intelligence, as this is probably the most broad definition we have here. So probably one of the definitions we can provide for AI is any technique which enables computers to mimic human behavior, or say it a little bit more informally, to think like how we think, right? But if we also make computers enabled to learn like how we learn from data, as Alex just said, that would be machine learning. And now if that learning happens with the help of some algorithms that we call neural network, that would be deep learning. Now these three kind of definitions could be a little bit confusing. So let me give you an example to make it a little bit more clear. Suppose that you are going to write a program, or better to say, to code a program that is going to play chess with the best chess players in the world in order to beat them, right? Now, you think about how to do that, and the first solution that comes to your mind is that I'm going to think about all the different movements that the opponent can make, and then I'm going to tell my computer program that depending on the movement you saw from your opponent, here is what you need to do. If it, for example, moved its pawn 2 squares forward, then it's going to be this move that you need to do in order to, to keep the game going or maybe beat your opponents. Now, this is definitely something that, something that we usually do in our work, in our, routine chess playing, and now we have asked or we have enabled the computer to do. And this could be regarded as something like AI. But it is not something as machine learning, because the machine, the model, the computer has not learned anything. We have hard-coded that program. We have actually told that program to do X and Y if the opponent moved A or B. So this is not something that the machine is learning by itself. Now imagine another type of program in which we provide a lot of good and bad chess games to a computer model or to a computer program. And we don't tell the model or we don't tell the computer program what to do. We just ask it that, hey, go through these games, try to look at them, learn from them, and gradually understand by yourself that what movements should be done in front of your opponent if you want to win the game, right? This could be regarded as machine learning. And as I said, if this type of learning happens based on algorithms that we call neural networks, then this is going to be a deep learning model. Now, when we define deep learning, we can also define something that people usually label as conventional machine learning, which basically denotes those algorithms in the machine learning world that are not deep learning. You may currently have some sort of doubts or questions about neural networks and what these algorithms are. So wait for a few seconds. I'm going to talk about them and try to introduce them to you so that we can now understand these kind of definitions a little bit better. Now, let me start with another scenario. Just imagine that we are going to train a simple logistic regression model. So you definitely have heard about simple logistic regression. This is a kind of, machine learning regression model that helps you to come up with the answer, which is, between 0 and 1 in order to understand or discriminate two different situations or conditions for your problem. Now, I have put something imaginary here. Suppose that you want to predict the probability of death in COVID-19 patients based on their gender, age, and their white blood cell count at the admission time. So this is not something very clinical. I just put something there to, keep the conversation going. Now, you can hypothesize that based on this problem, a linear equation like the following may be able to predict the answer, right? This might be a linear equation. We do have x1, x2, and x3 as our input variables. So these would be numbers. And then we have 3 coefficients, w1, w2, and w3. And we do have a bias term here. And altogether, they make a linear equation. So we can assume that if we train our model in a good shape, if we have enough data, if we know the clinical context, if we are good programmers, if we have good software, at the end of the day, we would come up with some values for W1, W2, W3, and B in a way that the result of this equation could either be prone more towards 1, which, suppose if the patient is going to be alive, or 0, which may mean that the patient is going to die. So this is the kind of logistic regression, simple logistic regression that you could rely on many software to do for you, like CSS, R, whatever other tools that you may use in your statistical testing. Now, the point is that these W1, W2, and W3 are called usually the parameters of the model. And this is a term that you mostly see in the world of machine learning. So I'm going to name that here for you, and I'm going to use this term from this point on in my presentation. The thing that I would like to know is that, although adding more data to this kind of problem that we are going to solve with a simple logistic regression would initially help the model to get better, more powerful, it would be a moment that adding more data is not going to help anymore. So basically, it would have a capitation for it, right? Adding more data is not going to help this model because we do have limited number of parameters here. The problem here is that W1, W2, and W3 are only 3 parameters. And if you also add B, there would be 4 parameters. So how do we know that the problem we have at hand and we are trying to solve is as easy as being solvable by only 4 parameters and a simple linear equation? So with that in mind, people thought about some other algorithms that were the annotators of current neural network or deep learning models. Now, let me change this very simple problem to another problem that we can now solve by a 3-layer neural network. And this is going to be a super simple neural network. There may be some numbers on the screen, but don't be confused. This is the only slide that I have in our today's presentations that is going to be a little bit mathematical like, but this is only for your sake of understanding, and I try to keep it as simple as possible. Now, imagine that I am building some equations based on each other. Imagine that we do have our x1, x2, and x3 as we defined in our last slide. And now I'm going to create 3 different equations. Each of them are going to receive this x1, x2, and x3, but they have different parameters, and they are going to result in different outputs. I do have a function called A here, which stands for activation, and basically in the world of neural network and deep learning, denotes some sort of non-linear functions like sigmoid, like ReLU, or whatever function that you may have heard about. And then I say that, okay, now that I have these 3 y1, y2, and y3 based on these 3 preliminary equations, let me put them into new equations and now try to add more weights here, like W10 to W15 and B4 and B5. And of course, I'm also going to add 2 more nonlinear functions here so that I make sure that these, the kind of results here are somehow different. And this is something important to understand. If you're a little bit think about that in mathematics, you would understand that if we don't put these activation functions here, then somebody smart would raise his hand or her hand and say that basically it wasn't needed to put all these 5 equations here without activation functions, because all of those could be again summarized in the form of one simple single equation. So the reason that people usually rely on these activation functions is that we really want to have independent equations from each other. And now finally, let me also add a final equation here that looks at y4 and y5, these intermediate outputs that we had here, and now it's going to generate a final output, which I call yf here. And this yf is going to be something you're looking for, like the probability of death or living after being diagnosed with COVID-19. Now, with this in mind, we can see here that we have some sort of terms here. So again, to review, x1 through xn here through x3 are our inputs, which would be age, gender, number of WBC count of the patient. These W's and B's stand for weights and biases, and together we call them parameters. A's stand for those kind of nonlinear functions. And then we can also have some sort of nodes and nodes that I'm going to show you in a second. But before that, let me just very, very naively show you how these all work, right? So I just imagine that I am going to work with gender 2, which supposes male. I am going to get the age of the patient, simply divide that by 100 and put the number as x2. And then for x3, I'm going to get the WBC count and divide that by 10,000 and put something there. And for all the activation functions, I'm going to use the same sigmoid function. And as you see here, it seems that if I start all my W's and B's quite randomly, which is something that not this simply, but something similar to that also happens in our day-to-day neural networks. We usually start these weights randomly. You would see that even with some random values for these weights and biases, we would finally come with YF that is something that the model has predicted. So definitely, if we start all these weights and biases randomly, there is no meaning for this 0.78. It doesn't mean anything, right? But we can hope that if we train this model, if we gradually teach this model how to tune its weights and biases, then as the time goes on and we keep training our model, this final YF would be something meaningful. Now, before I pause for questions, I would also like to show you this kind of representation of the equations I just talked about. This thing you see here is called a 3-layer neural network. Now, as you see here, we do have 3 input variables to that. And as you see, we do have some sort of nodes here, which are y1, y2, y3, y4, and yf. So basically, you see different layers of neural network. And these are the terms that you probably have heard a lot, right? People talk about neural networks. They say that, well, we designed a neural network with 10 layers, with 2,000 nodes, things like that. So let's keep everything simple and say that when people talk about things like layer and nodes, they simply mean that how many equations they have put in place and now how many equations are needed to finally get that YAF they are looking for. Now, this is something super, super simple, but this is basically the standard neural network, the base of whatever deep learning world is actually currently based on. Now, if you go advanced and look at deep learning models that are already out there, you would usually see a lot of those weird shapes like the ones you see on the right? These are the kind of neural networks that you see in different engineering papers and more recently in even health-related or medical papers. People say that we had been working on a neural network, this had X and Y architecture. You can see the architecture in the figure and you look at those figures and you see all these circles and lines connecting to each other and you wonder what those lines and circles mean, which basically mean that they have built their own very, very large equation. Every neural network is actually an equation, right? But these equations are not based on the very simple fundamental concepts you and I have learned in high school. Basically, they are very, very complicated and big, consisting of a lot of parameters. And this is the reason that our minds cannot naively understand them. We cannot process them by ourselves. We cannot solve these parameters by writing them on papers. And this is the reason that we are dependent on some sort of computer-based processing units like CPUs or GPUs to go through these networks and try to work with them. One last point is that, as I said, we start these parameter values quite randomly, right? We just pick some numbers, put them as W's and B's there. But you might ask, okay, how does the model learn at the end of the day to find the appropriate or at least the optimal values for weights and biases? This is where our data plays its role. We show the model a lot of data and a lot of labels, for example, that we might expect the model to produce for that data. And we let the model figure it out for itself. What values should be placed as W's and B's so that the final predictions of the model match the labels that we already provided to that model. And this kind of calculation is based on some mathematical context, which is mostly based on gradients, but I'm not going to talk about that. I just wanted you to know that deep learning is nothing but a series of very, very large and complicated equations and some data we provide to the model. The model look at the data, iteratively and gradually learn how to reduce its own error for predicting the labels that we ask it to predict, and finally find some optimal values for weights and biases. And then we pick that model, we freeze those values of weights and biases there, and we put it into real practice. We said that now we have a model, so if some new COVID patients come up, we just ask for their age, we just look at their gender, and we put the WBC value of their admission time in our model, and then the model is going to predict something which we hope is going to be valuable and meaningful. So I'm going to pause here, let you, Alex, or others to raise questions, concerns, and Alex, please feel free to compliment what I said, or complete it what I said. And sorry, I said compliment, I mean complete. And then try to add whatever you like, or ask questions if people have any.
Nothing but compliments, Puriya. So if you have any questions, please feel free to put them in the chat. And while we're waiting, so I have one question maybe you can clarify. So as you talked about, these deep learning algorithms are significantly more complicated than your machine learning. There are many, many equations that you threw out for the deep learning versus the logistic regression. So can you give us a sense of why would you select one family over another, and what are the relative advantages and disadvantages of machine learning versus deep learning?
Well, yeah, I mean, so that's something very interesting, and at the same time, very difficult to answer. So basically, you see this trend that nowadays when people, even data scientists, even experienced data scientists, when they face with a problem, they are somewhat tempted to say that we are going to work with deep learning models because they look to be much, much more powerful based on these very simple discussions we went through, right? They are based on more parameters, so basically, they are expected to work better. However, this is not the case. So there are a couple of bottlenecks there, and the easiest one to mention is data, as you said it yourself, Alex, in the beginning. Deep learning models, at least nowadays, are pretty much data dependent. They need some data to be able to learn something. We do train, and we can train deep learning models on very, very small data sets, but the result is not going to be something desirable. And I'm going to talk about that very shortly. But the point is that the first condition that you should have in mind when talking about, when choosing between deep learning or machine learning, conventional machine learning, is the kind of data set you have. Is that big enough or not? The other thing that I usually and naively rely on is that I go through the literature and try to look at what others have done. If nobody is using deep learning for a problem, yes, you might be quite innovative, someone that is going to, show the world something novel. But I would say that that is only 1% of chance. 99% of chance you're missing something that nobody else has actually applied deep learning on this kind of data set that you're interested in. So go through their papers, understand their limitations, what had been the reason that they have not worked with that. And sometimes I should also like to mention that these machine learning models, they do have some advantages that deep learning model lack. One of them to name is that most of the conventional machine learning models, they are explainable. We can look at them and we can understand how they are making their decisions. But this is something that people usually name as one of the disadvantages or weaknesses of deep learning. People say that these models are black box, and the reason they say so is that these models are actually based on a lot of parameters, and even we know the values for this base, we can look at them and see, oh, I cannot understand how the model actually made its decision. There are definitely techniques for understanding or trying to visualize the decision-making process of these models, but this is not something always reliable. So some people prefer to first try conventional machine learning, and if that works for them, this is going to be even better than deep learning. But if it doesn't, then maybe deep learning or a combination of DL and ML together could work.
Yeah, that makes sense. That makes sense. So I see we have two questions or two hands raised. So Dr. An, I think your hand went up first. Do you have a question?
Yes, two simple questions. First, I just want to make sure you say AI cover and machine learning cover deep learning is one of the subset of the whole picture. So what more than just like, for example, deep learning, what is a conventional machine learning?
Yeah. So
I just get confused. And AI is more than just machine learning and deep learning.
Yeah.
And AI covers something else.
Sure. Yeah, I can talk about that again. So basically, When we talk about AI, as I said, we mean something very, very general, right? So AI had been in place for decades. People have been working with that. But machine learning is actually those computer algorithms that learn from data. So in AI, you do not necessarily need to provide your code or your algorithm with data. As I said in that chess example, you could simply provide your algorithm with a set of rules that you have in mind, and you want your computer algorithm to apply those rules to real-world scenarios like you do. And this is going to be, again, AI, because you want your model to do something, or you want your algorithm to do something that you do in the day-to-day life, and they are going to mimic you as you tell them what to do. But if you provide your algorithm with some data sets and then ask that algorithm to learn from your data by itself, it's going to be machine learning. Now, deep learning is actually a subset of machine learning that is based on algorithms we call neural networks. They are definitely algorithms that are not neural networks and are still under the umbrella of machine learning. That, for example, simple logistic regression that I named is one of them. We do have a lot of tree-based algorithms like random forest, gradient boosting machines that you probably have heard about. These are all the kind of algorithms that are, even very powerful, and we do use them in many problems, but they are not based on neural networks, and for that reason are not considered deep learning. So what sets deep learning apart from machine learning is the usage of neural networks in the algorithms.
Okay, thank you. Let's get to the neural network there. So the solution for the parameter for the bias, are they unique, or it depends? For example, I have a given set of data. Depend how I enter the data in different sequence. Are they going to give you the same answer, or because depends how they receive the data in sequence, they may end up with different answer?
A very good question. So the point is that these deep learning models are actually very powerful to be less sensitive to how you input your data to them. So let me generalize the question a little bit. We do have a term in machine learning that we call feature engineering. And by it, we mean that whenever we want to feed some input data to the models, we need to be super careful of how to pre-process that data. Something like what I did here in my example, just to make these numbers work for you. In machine learning, these steps are pretty much sensitive. How you pre-process the age, Are you going to divide that by 100? Are you going to put the raw age there? Are you going to change the WBC count, something like that? Are you going to first let your model see the gender of the patient and then the age of them, or vice versa? These kind of questions might change the power of machine learning models and their prediction ability. In neural network, most of the time, not all the time, sometimes we do pre-process our data for models. We do care about how we feed our data to the model to make the learning a little bit easier for the models. But most of the time, considering you have enough data, these things are not that much important for deep learning models. And that is one of their advantages over conventional machine learning.
Thank you very much. Wonderful.
But just to make sure, I think, Kayan, you were asking, like, are you always going to get 0.45 as the weight as W0, for instance? Is that your question?
Correct.
Yeah. So the answer is no, you won't. And even if you feed it the identical data, it could be different. And for instance, there's initialization, right? How you start with random values. And so depending on what those random values are, it will ultimately potentially result in different values or weights here. And that's important because it would be nice if for instance, when you split up the data and do something like a cross-validation, that you could combine all the models together. And if the weights were totally predictive, you could do that. But unfortunately, with deep learning, they're not. And so even with identical data, probably if you had the same initial conditions, you would get the same weights. But there are other random pieces that you'll learn about, things like dropouts. So there are a number of cases where random components come in, and that's going to change what those values are.
Okay.
There's also the other aspect too, in addition to that the weights might vary dramatically between two different model fits, but how the model is estimating the outcomes will be very similar because of the high dimensionality of the fitted, or of the intermediate fitted spaces. So we shouldn't be looking at the individual weights, but really looking at input versus output when evaluating these models.
Right, and so Poria was quite correct in his answer. He was answering about the performance, and I think your question too is pointing out the performance should be similar given similar data, but you can't count on these individual weights being the same.
Okay.
My question is about weights too, and I guess I'm thinking. Let's say you have a sex, a disease that's has sex as a biological variable. So let's say breast cancer. 90% of breast cancer patients are female, something on that level, right? So, what would you provide that as a weight, for example, to sex? And when you start one of these neural networks and these equations to say, okay, the weight for gender or weight for sex is going to be 90%. Do you use some of that established knowledge when you start some of these neural network?
Well, yes, we definitely can do that, Dr. Westendorf. So the point is that, so correct me if I'm wrong, but what I understood from your question is that can we somehow combine some of the knowledge that we already have about these input variables and ask the model to work based on that knowledge in addition to whatever it is going to learn by itself, right? Okay, so yes, we definitely can do that. There are some techniques for that, how to weight these variables when they are entering. And we do have some new algorithms that are actually working on, this is a pretty much hot topic there, how to combine these black box of deep learning with some sort of algorithmic based rational thinking kind of models or algorithms that they can work side by side so that the kind of knowledge that we have in the real world could be combined with these sort of black box knowledge that the model would learn from the data. And then all together, they come to a value. Yes, this is a very hot topic, a very good question, and something that we do think about every day when we train some neural networks.
Great, thank you.
Yeah.
So Poria, I have a question regarding the sigmoid function.
Yeah.
What is the role of this function here in your example, and does that depend on the X variables?
Oh no, actually, sigmoid function is something that, so if you Google sigmoid, you would see the shape of that this is actually a kind of function that brings whatever input variable it sees to somewhere between the range of 0 and 1. So the main intention of using sigmoid here is that to make sure y1, y2, and y3, y4, y5, and y, all these output variables that we have, all y's, are always between 0 and 1, right? It wasn't necessary for me to use sigmoid. I could have used other other kind of nonlinear functions here as well, but I just put it there to make it a little simpler. But you would see sigmoid being used in neural networks or even other machine learning methods a lot, because this unique property it has, which brings values, input values from whatever range to somewhere between 0 and 1, is something very desirable, right? Whenever we want to differentiate two different conditions from each other, like living and death, or any other dichotomous condition, then a sigmoid function is something somehow valuable to think about. So this is something as an example I put here, and what it does is that it brings value between 0 and 1.
Yeah, more generally, you needn't have a sigmoid or something that's even bounded by between 0 and 1, except for the final step here. But a nonlinear function, as Puriya mentioned before, if you didn't have some sort of transformation there, you would end up with a linear function where the intermediate stages would have no meaning. So what you do is you introduce some sort of nonlinear function so that you can hit or model to generally shaped spaces and describe almost essentially any type of high dimensional curve.
Yeah, thanks. Perfect. So Alex, should I proceed or are there more questions there?
I don't see any more questions, so I think we can proceed.
All right, so we talked about deep learning, and now I'm going to ask a second question, which I expect some discussions coming up after this one. So my question is that, are machine learning and deep learning models different than statistics, or are they the same? So again, I would like to hear a little about, from the audience, those who agree that these are the same things, could be explained by each other, or those who believe these things are different, and then share your answers, and then we can talk together about that.
To me, the example you give, I thought was in statistical. That's what they call doing the transformation. You have set of data, you can recombine the data. It's just like you have x1, 2, 3, 4. Then you define y1, 1, 2, 1, 3. Then we regroup. So that is one approach, also like a principal analysis. You can find out what are the combination which will best discriminate the data set. To me, that part seems to be similar, but probably this definitely is much more powerful. They can regroup them automatically.
All right, so let me ask my question another way. Can I draw a bigger umbrella, like how I drew this artificial intelligence box around everything, and said that machine learning is going to be inside that? Can I do the same thing with statistics and say that machine learning is also completely inside the umbrella or area of statistics? Any questions or answers? Well, I can proceed, but don't expect me to answer this question, because this is something very challenging. And this is the question that I need to raise and then run away from you, because I'm pretty much sure that somebody would disagree with whatever I say. But I'm just going to, say a few words about that. The kind of routine answer to this question is that statistics and machine learning are neither exactly the same nor completely different from each other. They somehow stand on a spectrum, and while statistics mostly try to confirm some assumptions, to test some assumptions that we have, machine learning deals with prediction and understanding that, what would be the values for some variables if we, have some input variables. Now, this type of distinguishing between statistics and machine learning is not something quite accurate. Definitely, there are examples that can be can actually have machine learning work on some sort of confirmation or statistics on some sort of prediction. But at least this is how we can simply explain that. So the reason that I raised this question here is that it's not that I wanted to provide a definite answer to that. I just wanted you to think about this a little bit. And I know that some people who are currently present today I've talked with them a lot about this question. So this is something, again, that people talk a lot about, discuss about that, and data scientists, somehow believe that the statistics and machine learning might be different or similar. Just think about that. But for our own purposes, and maybe in the setting of these 4 workshops that we are going to go through, statistics and machine learning could be set apart by saying that in machine learning, we mainly focus on predictions. In statistics, mainly focus on confirmation of assumptions. But I know that this is not an accurate answer. So if you think that there are examples that are going to disagree with this explanation, you're 100% right. We are just going to assume simply that we are accepting this kind of differentiation between the two.
Yeah, so Walter says ML and DL algorithms all have a statistical basis and are routinely taught in stats programs. I'm going to come out in agreement with that. I'm a little biased because I'm from Department of QHS, but I think, so some of the dichotomy came from, some of the early breakthroughs in deep learning came from the computer science field for whatever reason. And so I feel like sometimes they get treated as separately, but in fact, so deep learning algorithms are derived from machine learning algorithms. And almost all of our machine learning algorithms have some basics in fundamental statistics. So I do see them as sort of on the same spectrum.
Yeah, thanks. Yeah, I was actually waiting for Walter to say that. And
I think it's, you probably were. I think it's also interesting too. I mean, the computer scientists who were doing work in this area decades ago, and I mean, people working with deep learning models in the 90s quite a bit, but because computational difficulties, they weren't able to bring them so far. But I mean, they were working with statisticians and really drawing from other fields to not have to redevelop or refine the wheel in every regard. So it's an interesting field. It's really expanding now.
Yeah, sure it is. And thank you, Walter and Alex, for that. So I'm going to speed up a little bit here, as far as I saw that 45 minutes has already gone, so we need to go through that a little faster. But anyway, so talking about the statistics and machine learning, regardless of how you consider them similar or different, there are terms that basically mean the same thing in both domains, but they do have different terms there. So this is something that if you're moving to machine learning from a more statistical background, you should have in mind, or at least learn about these terms, or vice versa. And there are a lot of examples here. You could further on go through this table and look at that. Some of the most common differences is, for example, this concept of parameters or weights here that you saw. Machine learning, weights is actually a little bit more common, parameters for statistics. Again, 2 other common ones here is sensitivity, that in machine learning, we usually use the term recall for that, or for example, positive predictive value, which we do have the precision term in machine learning for it. So there are different things and terms here. So if you are moving between these 2 fields, just make sure to familiarize yourself with these tiny differences, because when you go through the literature, they are going to use different terms there. Now, with that said, I would like to start talking a little bit about applications of machine learning and deep learning in different areas, or at least the 3 areas that Alex and I and others are going to cover in these workshops. So the first one for tabular data, this is the kind of routine clinical data sets that you might have in your department or for your projects. We definitely can use machine learning for doing some sort of predictions on these input variables, like, for predicting the diagnosis, prognosis, or, for predicting the values of some sort of variables, modeling data trends, and even imputing the missing data. So all of these could be used, could be solved using deep learning or machine learning. And we do have techniques for that. Just wait for that session that we are going to talk about all these algorithms in detail. Now, talking about medical imaging, which is something that Alex and I are both a little bit more interested in, we do have a lot of examples for how we apply machine learning to medical imaging. So you can see that, for example, we can use machine learning or deep learning to build different sequences of MRI from each other. Say you have T1 weighted and you want to create T2 weighted MRI out of that. Or you can use some deep learning algorithms to very accurately find the tips of these vertebral bodies here for you, so that you can further on use them for some sort of measurements. Or you can train some sort of segmentation or organ segmentation deep learning algorithms to very nicely segment the different organs present here in CT scans or even other modalities. And these are some sort of examples, but we do have a lot of examples of that happening through Mayo Clinic that I'm also going to talk about that very soon. Now, the third area is actually medical text analysis. This is something that you might have heard a little bit about, because I know that a lot of text deep learning algorithms, or as we usually call them, natural language processing algorithms, are already put in practice. We use them for searching for different pieces of data or information. For example, we use NLP or application of machine learning in text data to find diagnosis, procedures, symptoms from the very unstructured text data that we have from physicians, or what we have in EPIC or EHR, for example. We do try to use these algorithms for mapping clinical concepts and diagnosis to each other. We can have an algorithm that goes through some sort of surgical notes and try to understand if that patient is, for example, more prone to a kind of complication of that surgery or not. So things like that happen in the world of text analysis using machine learning and deep learning, and it's a very, very big and interesting world for itself. So we do have a full session to talk about how NLP is actually applied to medical fields and how it works there. Now, in addition to that, I'm going to talk about, as I said, about a few papers or a few studies that have been published in recent years from Mayo Clinic in application of deep learning or machine learning to medical fields. So I start with this one. This is actually one of Dr. Martin Kramer's papers, which we use natural language processing algorithms to identify common data elements in operative notes for knee arthroplasty. Very interesting paper. I guess Dr. Salim is also present here. So if you had questions, you can go to her. We do have another paper here that forecasts seizure using intracranial EEG measures. So basically, this is something that uses a non-deep learning model, a support vector machine, a kind of conventional machine learning model to go through EEG data and try to forecast some sort of variables there. Again, we can go through this very interesting paper from Alex himself. So this is actually one of the very, very nice papers of computer vision applications to medical data. It's a little bit weird that I'm trying to explain this paper when Alex is here, but the goal of the paper is actually to segment different organs of the body, or better to say different tissues of the body, using the deep learning algorithm. And this kind of application, this kind of model, when in place, then can be used for a lot of further machine learning or deep learning algorithms to rely on these very accurately segmented tissues or organs to come up with some sort of other prediction. So actually, what Alex did, and I know that other papers actually came up after his models, that they have built a kind of fundament or a kind of basis for a lot of further applications or secondary applications of deep learning or machine learning models here. Alex, you want to say something about your own work here? Because I didn't want to cut it short.
I will proudly say this falls under the category of low-hanging fruit. So this is an algorithm essentially that can segment out the fat compartment and muscle compartment from CT. So it's not a particularly difficult task, but if you were to ask a person to segment the image on the right, that would take upwards of 20 or 30 hours for them to complete. And it's something that a machine learning algorithm can do just like that. And so then once we have these, measurements of obesity and frailty, those correlate to patient outcomes for a number of different conditions.
Thank you, Alex. And then finally, I guess I also have one more, but this one is also, as I remember, one of the earliest models that was actually put into real practice at Mayo Clinic from a friend and colleague of mine, Dr. Tim Klein. So he actually used deep learning in order to fully segment the polycystic kidney disorders that we have in patients. It's kind of a renal problem or kidney problem. And now we are, Alex, please correct me if I'm wrong, but I guess we are currently using this model in real practice, and also your own model, right? Both of them are actually put into practice across Mayo.
Yes, that's correct.
Perfect, yeah. And then finally, here is one of my own papers here in which we train the deep learning model to go through some AP and lateral pelvis X-rays or hip X-rays, and then try to segment different parts of the image for us, and then we use those parts in order to measure some variables that are important for understanding the quality of the total arthroplasty surgery we did, and then the kind of patient outcomes that we should wait for. So this one is also published, and we recently published another paper based on that, which, as Alex said, used this algorithm to save a lot of time. And then we went through about 700,000 of X-rays that we had in our registry using this algorithm in 4 hours. And then based on that, Dr. Weiss, who's here today, and another friend of us actually trained, or better to say, analyzed the different variables of these parameters we measured here, and tried to come up with some sort of answers to important clinical questions. So deep learning models do not need to answer clinical questions directly. Sometimes they just set the scene, as Alex said, for some other statisticians or data scientists to come up and find access to data to which we didn't have any way to understand them before, and then use that secondary data to actually come up with some sort of real answers. These were some examples of how we applied machine learning and deep learning to clinical problems across Mayo Clinic. And you can find a lot more if you just simply try to search for that or Google that. With that in mind, I would like to start talking about another terminology in machine learning that we are going to see a lot. And this is something that we need to talk about in this very first workshop, because I'm pretty much sure the 3 other workshops would all come back to this terminology. I'm going to talk about something that is called the terminology of fit in machine learning. And you probably have seen all these kind of phrases before. To train a machine learning model on data mostly means to feed a machine learning model to that data, and also means to have a machine learning model learn from that data. So training, learning, fitting, they all could be used in the same essence here. And then we have terms that are called underfitting and overfitting, and they somehow stand against an appropriate fit of the model to a data. Let me clarify myself by showing you a nice picture here. Imagine that we want to train a simple machine learning model to distinguish the area of the screen that belongs to the circles from the area that belongs to those cross signs there, right? So we can have different types of boundaries plotted between the two part of the screen. The one that you see on the left-hand side is just a straight line there. It seems that it is not that much accurate, or a kind of powerful boundary between the two, because a lot of circles happen to be on the wrong side also, and also a square signs, the cross signs also happen to be on the circle part, right? So this is not something very powerful. We call that underfitting. So basically this model here that tries to draw a line there is actually a model underfitting to the data. It's not as powerful as it could be. On the right-hand side, we have another model that looks to be pretty much overfitting to the data. And by that, we mean that it is not even ignoring the noise in the data. I mean, yes, we probably could say that the model started very nicely from the top, and it tried to distinguish crosses and circles together, but it should have understood that probably these two cross signs here are only noises. So it's better to just ignore them and try to stay, try not to change the boundary based on those two. But the model didn't do that. And as you see here, now we have this weird machine learning model that is trying to separate all the crosses and all the circles in our training data. But the danger of this model is that if we try to apply that into real scenarios, it is not going to work as good as a model that we expect, because it's going to easily be deceived by whatever noise it might see in real world data, right? So this scenario is called overfitting, and it means that our model is too good to be true. So it's another way of describing overfitting. And finally, we do have an appropriate fit here in the middle that, as you see, has done a very good job in differentiating the two classes. It has also ignored these two crosses here, which probably are only noises there. So this one here is actually a model that might have, I don't know, an accuracy of 90%, 95%, but we definitely prefer this one to the one on the right-hand side, which might have 100% accuracy in our training data. But it's pretty much possible that if we put this model into real practice, the accuracy is going to be much, much less than a model with an appropriate fit. So this is the concept of fit here. And again, before I pause for questions or comments, I would like to mention two things. Now, as Alex asked in the beginning of the workshop, there are differences between conventional machine learning and deep learning algorithms. One of them is that, not all the times, but sometimes, or better to say most of the times, conventional machine learning models are more prone to underfitting. Basically, they do not have too many weights or parameters, and that's the reason that they cannot be stronger than a certain threshold, than a certain limit. They have a capitation for the power they can receive in most of the times. And on the other hand, when we talk about deep learning, as far as they have a lot of parameters there, they are pretty much prone to overfitting. They are pretty much prone to memorizing our data rather than really understanding that. Imagine a student that you are going to teach about something, and you ask the student to look at the book and understand the concepts in that book. Now, you know that your student is pretty much smart with some imaginary magical mind. If your book is smaller than necessary, then the boy or the girl as your student would not even bother themselves to learn the book. They would easily memorize that. This is our routine problem with deep learning algorithms. Whenever we want to train some deep learning models, we need to have enough data points, or large enough data sets to make sure that our models are not going to overfit to the data. And one of the reasons that we usually need big data for deep learning models is this concept of overfitting. A small data sets, we can still train deep learning models on them, but we are very, very prone to overfitting. Now I pause here to ask if anybody has any kind of questions or comments to share with us.
Purya, I have a couple questions.
Sure.
So I'm not a statistician and I'm not also an AI person. So that's the problem. So, you know, in a statistics, there are so many assumptions, you know, that you have to make. For instance, whether the distribution is normal, sample size, all of that. So except for the sample size that's important here, are there any other assumptions that you have to make?
Well, I'm just saying on top of my head, so Brad, Alex, and others, please correct me if I'm wrong, but one thing that I know, as I said, is an advantage to deep learning models is that compared to conventional machine learning or statistics, you really have fewer assumptions to make, right? So this is something that makes these models very, very powerful. You need to deal with your data in a way. You sometimes try to pre-process your models in order to make your models, pre-process the data in order to make your models a little bit more powerful. But as far as I remember, there are nothing that I can say, I can't say very powerfully, but you know, there are nothing that at least I can remember very clearly that might be the kind of limitations similar to what you said for deep learning. We do need to change our data from time to time when we put it into deep learning. We do need to give weights to some data, input data. We do need to be careful about the relative size of different data sets that we have compared to each other, but not something similar to that. Alex, do you want to jump in? Oh, sorry, somebody else wanted to say something.
Oh, I would make a couple of comments, is that usually machine learning and even deep learning use a loss function and try to minimize this loss function. And these loss functions, and there are different loss functions for different models you fit, but generally they're taken from classical statistical theory based upon a particular type of distribution. So the idea that you have errors, constant errors, is something universal to deep learning as well as the machine learning and classical statistics. But you can account for that in deep learning just like you do in statistics. But the real thing about machine learning, including deep learning, is that they allow for very general curve fitting in high dimensional space. And a big part of machine learning and deep learning is looking at how much you can fit a model without overfitting it. That's really, I see this as a continuum from classical statistics, straight line, to a curve, to a more general curve in machine learning, and then deep learning even much more general. And I think a couple of the classical statistics or machine learning methods are random forest and gradient boosting machines that allow you to fit nonlinear curves very fluidly without pre-specification.
Thank you. And also, what sample size is considered a good sample size? For instance,
more is always better, right?
Yeah. For instance, the one that you showed segmentations that, you know, you might have CT exams like CT images of so many different reconstruction kernels, or they might be all from the same reconstruction kernel. So I'm just wondering what parameters are important in order to have like a good sample size or to come up with a number.
Yeah, so there are some rule of thumbs there that we try to think about when we want to estimate the number of sample sizes that might work for training a deep learning model, for example. The point behind that is that neither of these rule of thumbs are accurate. So the simple answer to your question is that before we start training a model on some specific data sets, we don't know exactly how many data would suffice for a good working model. We do look at the literature available to us, people who have done something similar to us. We also try to look at how complicated the task for which we are training a model is. And we also try to look at how clean or how distinguishable our data is. And based on all of that, and with using the general wisdom and experience of people who have already done that, we usually start with the size of data set. And most of the times, to be honest, the feasibility also plays a very important role there, right? For example, some people approach us and say that we have a data set for a problem. We want to use machine learning for that. And we tell them how many data points do you have. They say that, for example, 200 CT scans. And in this case, what we do is that we ask for all data they have and try to train something like that and see if the model works or not. If it does, but it's still not that much good, we just ask them for further data. But if it works very badly, very poorly, then we probably should say that either the model is not something usable for this data, maybe this is not a very good problem for machine learning, or maybe the number of data points you provided to us was too fewer than what we needed here. So there is no straightforward answer to that question as well.
Okay, thank you.
Yep. And I also see, Kai, you also have a question there, right?
Yeah, a naive question, but I just like Walter's comment. It's a fit in a higher dimension. That's probably a good term because this machine learning, they're unlimited. They can fit anything in higher dimension. But question for you, for when you analyze the imaging, do you have to digitize the imaging or you analyze the imaging by itself? I just cannot see everything is numerical. So I thought you have to digitize the imaging, like a pixel location, pixel size, and the grade level. Then they can do analysis.
Yeah, thank you for that question. I kindly ask you to wait a little for your answer, because I do that I talk about that, how to actually pre-process an image to be fed into a model, right? That was your question. And I have a slide to talk about that a little bit later.
Wonderful. So in that case, for your segmentation, do you have to go through a neural network or some other machine language for that purpose? A couple of papers you pointed out, either in the total hair or in the fat segmentation. Do you have to go through the neural network?
Yeah, those were all based on neural network as far as I remember, except that one that used EEG data. Others were using neural networks.
Okay, thank you.
I can't help but chime in on the sample size question because this is like the most common question that I get for new studies. And the truth is, it's really, really hard to tell. Unfortunately, we don't have something akin to the power calculation in statistics for measuring significance. We just don't have anything like that in deep learning. A couple rules of thumb I like to give. So if you have less than 100 images or less than 100 patients, it's really, really tough. So sometimes you can do something with that. In a lot of cases, it's just not going to be enough. For a typical project, I would aim between like 500 and 1,000 patients. Usually that's enough. Again, not always. These algorithms are really, really data hungry. And so I always say like the most data that we can possibly get, the better.
Thank you.
Thank you.
I guess, Brad, you wanted to say something?
Yeah, you've kind of approached it from a statistics perspective for the engineers in the group. Another way that I tend to think about it is that it's a signal to noise problem. If you showed me 5 images that were pure white and 5 images that were pure black, I could build a AI that would figure out white versus black. On the other hand, if you gave me 2 images that were, gray noise and another set that were gray noise, if it's truly noise, there is no signal and no amount of AI power, no number of examples is ever going to figure it out. So it comes down to how strong is the signal versus the noise will determine how many examples it takes to get an AI that performs at a certain level. So for the engineers, that's another way to think about it, and why we don't have a specific number. Every CT problem, it takes 236, for instance.
Thank you so much. That's very, very nice explanation of that. And you actually reminded me of another project that I remember we talked together about that. So basically, whenever you go through a project, you are somehow concerned about the area of the image that is going to have the most valuable signal for you, as Brad said, give you the most informative answer. So if that area in the image is pretty much small, then it means that you need to provide more data for your model, because the model is not going to find too many signal in each individual image. So probably you need to expand the data set you have to help your model with that. Thank you. And I see, Mariam, you have a question?
Yes, I have a question regarding the variables that affect the quality of fitting. So as an example, going back to using the ML for the image segmentations that you have already presented on. So for example, like you use algorithm for the one set of the data, as an example, the hip replacement, for example, implants, and evaluating the loosening of the hip implant or whatever in the proximal femur. And then you have already validated the fitting, like in terms of like how good was the fitting of your model for that data set. Could you expect you're gonna get the same fitting quality if you use the same algorithm for another anatomical site, let's say the proximal humerus, like similar for the similar applications, for example, loosenings of the proximal humerus implant or the reconstruction? Or no, like what are the factors? I guess I'm getting back to my main question. What are the factors that really affect the quality of the feeling or accuracy of your the algorithm for prediction?
All right, so I guess that your point is actually talking about the generalizability of our model's performance.
Right.
Now, the point is that it somewhat depends on the training data on which you are training your model. For that specific feature, that study that I was talking about, for example, here, what we did was that we did train a model only on pelvis X-rays. So our model did not see any kind of humerus X-rays, for example. So chances are pretty much high that if I feed in a shoulder X-ray to this model after it had been trained, it could actually mess up everything because it doesn't understand what signal, quoting Brad, is gonna find in that image, right? So the point is that you really should look at your training data. We don't, most of the time, expect our models to work good when applied to data that they that are totally different from the data that they have been trained on, right? We do want our model to be able to look at some sort of similar data which had not been in our training data and do the job for us, because that's the entire point behind this deep learning. We want a model that could look at some sort of new pelvis X-rays that it has not seen during the training and do the right job there. But if the input X-ray is gonna be from shoulder or from knee, then the model is going to mess up. So basically, it really depends on how you engineer your training data. Sometimes you might engineer your training data set in a way that it includes images from many different parts of the body. And in fact, you're looking for a signal that could be present in any part of the body, or at least in multiple parts of the body. In that case, you should expect your model to work for different parts of, for different kind of input data that is going to see after its real training. But for most of the cases, including this one that you mentioned, no, the model is not going to work if applied to any other X-rays rather than pelvis, AP pelvis, or lateral hip X-rays.
Okay, so that was like a huge variations, like from one anatomy going to another. But then, what about like a image quality or the imaging technique that was used for the similar, like for the same consistent anatomical side as the pelvis? You have a different imaging technique, so that is still, you're going to have that variability that changes your the reliability of the model, right?
Yeah, so that actually falls a little bit more on the gray zone. So the point is that we do expect the real images a model is going to see to have different qualities, or sometimes lower qualities than the images that we train our models on. And we even expect the images to be rotated in some degrees, or be a little bit noisier than usual. So these things are something that we think about, and we do try to make our models somewhat insensitive to these kind of variations in the input data. And we do apply some techniques, namely data augmentation, during the training to make sure that the model is able to still distinguish the noise from the real signal whenever facing even a very noisy image or an image with lower quality. So these type of variations, we do try to address them as much as possible. But again, if you feed a very noisy image here, the one that has a very different quality, but it's still a kind of AP pelvis X-ray to a model, chances are high that these models would fail. So that is the reason that in every AI publication, usually reviewers ask for your failure cases, right? They ask us that we should provide them with some examples of those X-rays, or CTs, MRIs, or even text data, whatever input data that we expected our model to work good on them, but the model failed. And then we should try to explain that failure, why it happened. Was it because of the quality of the X-ray? Was it because of the incompetency of the model? What was the reason behind that? So you're actually addressing a very important point in our training, the concept of generalizability, the concept of noise, and the concept of how the model can address the differences there. But the answer to that is, again, not determined yet. The model could fail some cases, could overcome some of the barriers as well.
Thank you.
So GOT asked a question in the chat. I want to make sure we don't overlook. So the question is the test versus training data ratio of data division optimal at a 2:8 ratio?
Oh, no, that's not the case. So basically that 2:8 actually, it's kind of a heritage from the conventional machine learning ages. So whenever you are dealing with different models, different algorithms, the strategy you have for splitting your data to training, test, and validation completely depends on that specific problem for you. These kind of questions are actually problem specific. And I can give you an example. For example, imagine that you are training a deep learning model on, I don't know, 200,000 of X-rays. So in that case, you really do not want to spend 0.2% of your data for the test set, or I don't know, for your validation. What you do is that you may take only 0.1, something like that. I mean, something very, very small part of fraction of your data only for splitting. So those numbers, they are somehow general rule of thumbs, but they are not correct in all examples. We need to be flexible. We need to look at the data and the problem we're working on.
Yeah, makes sense.
Yeah, I would try to proceed for the time concerns and see how far we can go here. Now, I'm going to talk about variations of different machine learning strategies, training strategies like. So this is again something that you would hear a lot when you go through the literature of machine learning and deep learning. Some algorithms are called supervised, some semi-supervised, some unsupervised, and some self-supervised. And just for your information, we also have a reinforcement learning category that stands at the 5th category here. But as I said, I'm not going to talk about reinforcement learning for these workshops purposes. Now, I'm going to briefly introduce all these 4, and then we will again pause if somebody wanted to say something. For supervised learning, our assumption is that we have labeled training data, which means that all data is labeled by humans, right? And then the model learns to predict the labels on unseen and unlabeled data. Let me give you an example. Say radiologists pick 2,000 chest X-rays, some with pneumonia, some without pneumonia. The radiologists themselves label the entire data by looking at each X-ray, saying if it has got pneumonia or not, and then we train a model on the labeled data to differentiate an X-ray with pneumonia from a normal X-ray. So this is something relatively easy and straightforward. And this kind of maps, heat maps that you see here is actually one of those techniques that I mentioned earlier, could be used to visualize why a model made a certain decision. For example, if the model says that, oh, this here has, I don't know, pneumonia, maybe it had found some sort of opacity down there that it is actually showing there. Now, this is the kind of supervised learning model, right? You have your labeled data, all the data is labeled, the model look at the data, look at the data label, tries to be as accurate as you in making the predictions. Now, we have another type of training strategy that is called semi-supervised. In this strategy, we again have training data, but only part of that training data is labeled. So in the previous example, just imagine that we still have the 2,000 chest X-rays, but our radiologists didn't have time to try to annotate all the X-rays. So they only went through 500, the first 500 of the X-rays. And now we want to train a model using that 500, but at the same time, using that 1,500 unlabeled data that we have, right? This is going to be an approach called semi-supervised training of a model or learning, right? So again, the kind of final output of the model we expect is going to be the same, but the labeling approach of the input data is going to differ compared to the previous scenario. Now, in self-supervised learning, something really interesting is going to happen. We do have training data, but no training data is labeled. And the model tries to actually learn to predict some sort of automatic labels for the data. Now, how does that happen? Imagine we do have that 2,000 chest X-rays here. What we do is that we try to train a model that can, if for example, someone like myself put a black box on part of this chest X-ray, the model can then look at that and say that now I can fill this box for you and give you a picture that looks like the original X-ray, right? So here, we do not need any labeling, right? Because the label of this black box is actually the original image itself. We do have the original image. We just simply put a black box somewhere on the image, and we tell the model that, hey, we didn't want to annotate anything for you because you already have the label. Just look at the original image. That's the label for you. So in self-supervised learning, the term self-supervised comes from the fact that the model is actually finding the labels from the data itself. And it could happen in different scenarios. One of them is this example I put for you here that is called in painting approaches. And it certainly has some sort of applications for itself. For example, when you try to repair some old photographs using Photoshop, the kind of algorithm that happens behind the scene is something similar to that. But it also can have some sort of applications for medicine that I can talk about a little bit later, or try to provide some examples for you when we reach that checkpoint. So you might say that, how is that going to help the fact that we wanted to understand these chest x-rays had pneumonia or didn't have? And I can say that just have this question in mind. We are going to talk about it soon. And finally, we can have unsupervised learning. And in this unsupervised learning, we do not provide any training data, any training labels to the model again. So it's like self-supervised training, but we want the model to try to distinguish the input data by itself. So basically, there is no labeling here. So, in the self-supervised way of training a model, we did have some labels, but the labels were automatically generated, not human generated. Here, we do not have any kind of data. We just simply provide 2,000 chest x-rays to the model and say that, hey, there might be some differences. There are ways to categorize these 2,000 chest x-rays. So why don't you go out there and try to find a way for yourself to categorize them? And as you can imagine, there is no guarantee that the model comes back to us with kind of a differentiation between pneumonia and not pneumonia. It may come up with finding a way to differentiate between male chest x-rays or, for example, female chest x-rays. So model goes out there, all standalone by itself, independently, try to distinguish the data points in our data set from each other as far as it can. So it could be regarded as unsupervised learning. Again, some applications do exist for unsupervised learning, yet I would like to mention that supervised models are definitely the most common type of training that we usually see in the world of medicine. If you look at a lot of those applications papers out there in journals, most of them are supervised. Some use semi-supervised approaches because we do have time constraints in medicine, specifically if you want experts to annotate some data for us. So it's not something very unexpected that experts say that we can only annotate a part of the data for you. And we also use unsupervised and self-supervised models in specific examples that we can talk about a little bit later. So these are the kind of categorization of different training strategies that I would like to talk with you about. All right, but this brings us to our time of group work, which I would like you to split up to some groups. Alex, I'm not sure how many people are already in the chat. I don't see the numbers here, but we can figure out groups of 4 and 5 and using the Zoom capabilities, fortunately, and then have people think about the scenario that I have put here for you. The scenario is that imagine you have been asked to develop a machine learning model to predict the prognosis of COVID-19 patients admitted to Mayo Clinic based on their admission time chest x-ray. So somehow similar question like the one we discussed in the beginning, but this time the input data is going to be the chest x-rays. Now you're going to say, you're going to predict if the patient is going to have a bad prognosis, which basically means that he or she is gonna die or be admitted to ICU, or a good prognosis, which basically means that no ICU admission, unfortunately discharged out of the hospital. So just imagine that somebody has asked you to come up with a project plan for this kind of machine learning idea. What kind of key steps do you put in the workflow of this project? Where do you start? What do you do in the beginning? What do you do in the middle of the process? And how do you wrap up your project? As you can imagine, after this, I'm going to talk about the workflow of a machine learning project. So at first, I want you to think about that by yourselves and understand what these work might consist of what steps this kind of workflow might consist of. And then I'm pretty much sorry that this was a very short group work, and I'm sure we cannot listen to everybody or representative from all groups, but I'm pretty much eager to hear at least 2 people talk about what they went through their groups and the kind of workflow they designed. So feel free to open up your mic and say what you thought about this kind of group work.
I guess I can talk about it. We had a 5-minute breakout group, and we kind of went on, as you mentioned, like, what do you think is the starting stage and the middle and the end? So the starting stage, we kind of talked about how to get the data set and have a good amount of records which are labeled like X-rays, the patients who actually went to the ICU versus not over there. And then also the base resources that are available in terms of where actually to read in the data or analyze it and build the model, the platform, those things. And then looking at the basic demographics. Then in the middle part, we discussed about actually model development and what would be suited, which approach would be suited, like machine learning, deep learning, those things, and then having a base model, and then from the base model kind of going upwards, how much the model could be improved and what aspects could be improved. And the end product would be it being packaged in an interface where it's actually usable clinically.
So thanks for sharing, Habiba. So you brought up a really interesting concept, actually, which we do all the time in practice that I guess we haven't touched on, which is that sometimes you just need a minimum viable product, right? Yeah. You need to see like there is a pattern in the data here that's real that we can see. And so you'll train like a base model. And then, depending on the results of that, that's something that you can eventually improve. So I guess I'll challenge you or the group with a question of what do you look for in a base model? What would be an appropriate first step if you're taking on a new project that has a modeling component?
I mean, if there's a pattern in the data, like that is identifiable. I'm not sure, like certain clinical findings where you can get like a prediction out of the pattern that you see in the findings, combined with the like other demographics like the age. So like you factor in multiple parameters and then you can identify it clinically. So basically from that you can like sort of think that that's something that can fit into the model. I'm not sure.
Yeah. And something that we also talked about earlier in the discussion is how predictable the data is, if it's black versus white or something that's kind of both the things are similar. So kind of knowing where, how much the model is predictable, kind of that's what I was thinking in terms of base model.
Yeah, for sure. And actually, I would add that in some cases, machine learning algorithms are preferable to deep learning as a base model because in many cases they're more explainable. Mm-hmm. So if like we have a big clinical data set with 150 parameters and we don't know necessarily what's going to be important, sometimes we'll do feature selection with a simple machine learning model to try to narrow down, what are the variables that we think are going to be most predictive. And then once you have that data set narrowed down, then you can train something more sophisticated and you can be confident that the pattern is there in your data and you can focus on the modeling aspect.
That makes sense. Thanks.
And Bardia says, is there already a trained model available? Yeah, that's a really good point.
Very nice point. So Alex, would you mind if I proceed and go to the next slides as far as the time is actually passing, and I would like to finish before the time so that we make sure people actually listen to everything we have. Good?
Yeah, for sure.
Okay. So thank you. So basically the kind of steps that Habiba mentioned, most of them are actually included here and mentioned already by her. So whenever we want to go through a machine learning project, we need to think about several steps. I don't claim that the kind of workflow that I put here is actually 100% accurate or something that we always follow, but I can claim that what we do is most of the time similar to these. So you see the steps here. I'm going to spend a couple of minutes talking about each of those, introducing some concepts or resources to you about that. But before that, I would like to mention that the kind of machine learning development workflow is not something completely stepwise. It's not even something circular. It's a very iterative process. You need to move back and forth between many of these steps during the project in order to make sure that you are still on the right track. So we simply just put some steps behind each other here, but it's not going to be that much simpler in the real world practice. So just have this in mind, and we can then start talking about each of these steps and what they mean. Before that, a very simple poll for you that I would like to know your opinion about. This is not going to be time taking thanks to Zoom. So we simply can launch the poll here. Alex, can you kindly do that for us? So the question is that, thanks, which of the steps in an ML lifecycle will take more time based on the workflow I showed you before I jump through them? And I just want to know your opinion about this. This is not going to be something with a correct answer, something that probably all of us might have different answers to, but I would like to see how you think about that.
So we're at about 80%. I think we can.
Yeah, I guess we can pause here. So it seems that the majority of you mentioned data handling as the step that takes the majority of time, which is something that I am sure at least Alex, I, and Hillel and others here also agree with. But yeah, resource collection is also going to be time consuming depending on the resources you already have or the workflow you need to go through in order to ask for data from your upper hand institutes. But we can talk about these steps, and you hopefully would find a more kind of realistic understanding of what each of these steps actually consist of, and then how much time they need. So let me close the poll and then proceed with my slides. And start with step one, which is actually the problem definition. So the way that I would like to talk about each of these steps is that I would like to raise some questions for you. And these are the questions that you or your teammates need to ask yourselves whenever you proceed to one of each of these steps. So during the problem definition, there are three main questions to think about. First is that, are you focused on an appropriate problem for machine learning or not? So this is something to have in mind. Machine learning, deep learning are very trendy nowadays. So people, most of the time, and I see that, Dr. Gardner, Dr. Erickson, who are here, have seen a lot of that example, or other you who actually are involved in deep learning training. People approach you, they ask for problems to be solved by machine learning and deep learning. And the moment that we talk, you understand that the problem itself is not something that we at least usually apply deep learning to. I don't say that there's always a definite answer for a question that is suitable for machine learning or not, but this is something that you could think about, or you could go and ask people about it, whether or not your question is more statistical type of question or a machine learning type of question. Also, how much do you know about the clinical context of your problem? I mean, the question is that even though we can try training some machine learning models on some sort of data sets, does that really add any value to the real practice, to the real clinical practice? Because at the end of the day, you are training these models not for the sake of training, but for the sake of implementing those models in real scenarios. And for some of you, also for publishing them. And one of the questions that almost all the time reviewers of journals ask people who develop machine learning models is that, what was wrong that you decided to develop this model? What was that missing piece that you decided to address or approach using your model? And most of the times, it might seem very simple, but most of the times we are so much excited about the machine learning algorithm that comes to our minds that we forget thinking thoroughly about the clinical context and the real problem we are going to approach. And finally, it's really important to also take a look at the published literature out there, and even the gray literature, because a lot of times ML solutions already exist for you. Like the question Barry raised there, we should try to understand if there are already trained models for the kind of problems we are going to solve. And if they are very good working models out there, I do remember a mentor of mine, Dr. Filbert, once told me, if you found the working algorithm, the stupidest thing you can do is to try training a new one or coding a new one for yourself, because this is working so fine for you. So if something is already available, so just go there, grab it, and apply that, or at least modify that a little for your own data and work with that. Also, you can see the strengths and weaknesses of other people's work. So if you still decide to proceed with training a model for yourself, you can at least focus on powering your model in a way that it shines compared to the other already available ones. So this is actually regarding problem definition. And one thing I would like to mention here is this kind of database here, archive.org. So for those of you who might be more dealing with medical data sets, you might not have heard about this, or you might have heard at least to the medical equivalent of this, which is medRxiv. We at least in the medical world, we are mostly used to deal with peer-reviewed publications. This is not always the case for engineering and computer science areas. So in those areas, many papers are first published in arXiv, and some are only published in arXiv, which is not peer-reviewed, but it's still a very good resource of new technologies, innovations, specifically in programming and machine learning. So if you are searching in the machine learning world, if you are searching about some algorithms already in place, don't forget to check archive.org. Usually it has a lot of articles for you to at least go through and grab a notion about what you want to do later on. So that was it. I would pause at the end of each two steps to ask for questions or comments. But now for the second step, we are talking about resource collection here. So you have a problem, you are pretty much sure that the problem actually suits a machine learning type of idea. Now you need to go out there and try to collect the resources you need. And basically, the most important resource is your data, the data that you want to train your machine learning model based on. there are some questions to ask. How much data do you need? We already talked about this question a lot, right? It's not easy to answer that question. How easy is it for you to want access to clean data? A lot of time you can find access to data, but when you get that data, it needs a lot of cleaning. And this is going to be the most time-consuming part, as you would see later on, as you mentioned that yourself, right? And then, can you find access to any external data sets or not? We do have some external data sets in place for many of the routine kind of data that we work with, like for chest X-rays, like for different knee X-rays, or CT scans, MRIs, non-medical imaging type of data. So if you are a data scientist thinking of training a model, you will always benefit from expanding your data set. So if you have your local data, that's good. And if your local data is very, very large, you probably do not need any more data. Again, good for you. But for most of the cases, we do need to look for more data all the time. And in that case, don't forget to check the external public data sets that might be available, or external data sets that other institutes might be able to share with you. Sometimes you just assign those MOUs, you can use each other's data. So these things, data is actually the goal of machine learning. Don't forget to get as much data as possible. Then we need to talk about your expertise. I mean, if you are crafting a team to approach a machine learning problem, you definitely need both the domain experts and the programmers in your team. And you should think about how to facilitate the dialogue between the two groups, because sometimes these people are not used to talk with each other, and the kind of language barrier that might exist in the middle is going to hinder your progress very significantly. So it's good to have some plans for that, and it's good to orient people how to communicate more effectively with each other. And then finally, we can find access to some hardware requirements for our training. As I said before, these kind of new machine learning models, specifically deep learning models, they need some sort of hardware to train on, right? They are not somehow trainable with the routine computers, routine laptops that we work with. So you can either try to find access to some sort of local hardware, local GPU cards, for example, or you could rely on some sort of cloud-based computers or cloud-based resources that are available, and Mayo has recently invested a lot in that. So basically, you need to think about your hardware requirements as well. Now, talking about that, a couple of slides regarding step 2. First of all, some machine learning applications need a lot of data, namely the deep learning. We went through that a lot of times, and please don't forget that deep learning, at least nowadays, is dependent on data. There are NDVers in order to make it less data dependent, but we are still far away from that checkpoint. Second, data cleaning is tedious, but very, very important, right? Even for deep learning, we need to clean our data. I mean, if you clean, the more time you spend on cleaning your data, the better results you will get from the model. I remember once from Dr. Andrew Ng, who is one of the pioneers in this, deep learning world. He once said that, we already have enough models. We already have models with enough level of complexity. What we don't have is enough workflows for cleaning the data, preparing our data, pre-processing our data to be fed to our models. So don't forget that data cleaning is actually one of the main steps that we need to go through. And I'm going to talk about that a little bit more. Next, so NIH is recently putting a lot of emphasis on what data is actually considered good data. And they have this abbreviation for that, which is called FAIR. Stands for findable, which means that your data should be, the metadata of your data should be findable for both humans and computers. Basically, you need to have a way to search for the data, and that data should be searchable. And then that data should be accessible. I mean, if you found that data, you should be able to download that data and play with that. Interoperable means that different applications or workflows should be able to work with that data without needing to change their nature too much. They should be something pretty much in a level that everybody could work with. And finally, they should be usable. So we are looking for data that could be used in different type of projects. So if you're only aiming at collecting data, paying attention to FAIR might not be that much important for you. You still want to have access to FAIR data because you could use that in different projects. But if you're someone who is thinking of releasing your data for public access, then definitely you need to be able to FAIR and all its details. Just Google that and you will find a lot of interesting points there. Public data sets, I already talked about them. Just make sure that you go through the papers. There are some sort of review papers that have summarized the different public data sets that we have available for medical work. This one, for example, is a very nice collection of medical image data sets for deep learning. It goes through different disciplines, surgery, internal medicine. It just tries to capture all the data sets that have been released by the time of publication of this paper. And we do have a lot of other papers like that. Make sure that you do not miss that. Finally, Google Cloud and Make-and-Link AI Factory are the kind of resources that we have in place for training your models using Google Cloud resources. So as I said, for finding access to that hardware you need to train your machine learning or deep learning models on, it's not always necessary to have your own local resources. Those resources are most of the time very expensive. So one alternative way that is much, much cheaper if you are not someone who is working 24/7 with these models is that you could rely on Google Cloud or Maple AI Factory resources. Again, this is a full story behind that. We could talk for hours about what kind of capacities Maple Cloud has for us, but we are just going to touch that now and let you go through that by yourselves. Now I stop here, and I would like to ask for people if you have any burning questions to ask, and I emphasize on that burning term because we have only 15 minutes to go through the rest of the steps. Anything?
Poria, just one quick comment.
Sure.
More for the group that is considering publishing, and especially if you're going to a more clinically oriented journal. So orthopedics is a little behind the times compared to some of the groups that have used machine learning in more advanced ways, like cardiology and oncology, for example. So when you go and do a machine learning oriented project, think first if it's appropriate to answer the question with traditional statistics, and at the very least, also perform traditional statistics as a comparative metric. Nothing sort of drives me nuts more than opening Journal of Arthroplasty and seeing a new machine learning paper that reports, an area under the curve, nothing else, but doesn't show how that performed with traditional statistics. So don't abandon that. For the field to move forward, we really need to have these comparative analyses to know if there's a value add from the machine learning component.
Yeah, thank you so much, Cody. That is super important. And again, as you kind of said, deep learning, machine learning, neither of those are those magic bullets or the kind of hammer that we want to put on whatever nails we have. Those can work in some instances, definitely don't work in many other instances. So, and for some kind of problems, we do have both approaches, statistics and machine learning available. So it's good to compare them head to head and see which one works better for us. Thanks for sharing this, Cody. And then, so let me proceed with that one to data exploration, or something that people sometimes somehow call it DA, or data exploration analysis. So what we do is that we go through the de-identification of data. This is something that we need to do later on. And during the data exploration, you need to ask yourself how much of your data is already de-identified. There are a lot of ethical and professional issues behind that I'm pretty much sure you know more than me about that. So one thing that you need to understand about your data during that accelerated data analysis phase is to understand what fraction of your data needs de-identification and in what level, because sometimes data are identifiable in very, very different ways. So it's very interesting. I guess one paper from Maple recently came out, Hilal shared that with me, that showed that even looking at some head MRIs, some algorithms were able to understand who the patient was, right? So basically, just by looking at some MRIs or some sort of medical imaging, some algorithms might be able to understand the identification of patients. So just be careful with that. The second question to explore about your data is the distribution of your data. We should think about the heterogeneity of the data, and second, how much representativeness the data has. Okay, is that data something that you could further on rely on and say that if I train a model on this data, then it is going to be usable in real scenarios? Or is your data something that unrepresentative of the real case data? So in that case, your model would not be unrepresentative as well. So think about this a little bit, and also think about the hidden biases that might be there. I'm going to talk about biases in a separate slide. So let me say that most of the times when we talk about deep learning and machine learning, again, a kind of fancy trend is that people try to a fancy but still necessary trend is that people try to show how these models could be prone to different biases. And for example, they mess up with different kind of noises that might be available in the picture, or in their input data, or they might not have equal performance, or at least comparable performance between different genders, or between different kind of human groups. So these things are important, and you should really pay attention to that. You should think about your data first. Every machine learning model is as powerful or is going to be as good as the data it is trained on. So during your exploratory data analysis, pay attention to the biases that might be hidden behind your data. If you cannot address those biases, then you should wait for those biases to be also visible in your machine learning performance, right? So this is something to have in mind. And one more important thing is that this is not always the case that deep learning models mess up with the bias. Sometimes you could rely on deep learning models to detect the bias. And this is something very, very interesting and novel. And I really encourage you to go through this second paper here, an algorithmic approach to reducing unexplained pain disparities in underserved populations, in which they found out about one of the clinical biases that we human had in approaching some sort of patients with knee pain. And then they understood that when they applied a kind of non-biased machine learning model to the same population. So just go through the paper. This is going to be super interesting. Bias could be created by machine learning model, could be propagated by machine learning model, or could be reduced by machine learning models. All those situations could happen. Now, data handling, which definitely comes immediately after data exploration, and this is definitely the step that is going to take the most of the time, as you kind of mentioned, right? So we spent months on this step for every different project. So we do need to de-identify our data. I talked about that already. We do need to think about the different cleaning aspects that the data need. For example, we need to understand how to approach the missing data. Are we going to impute those data? Are we going to simply remove the cases that have missing data more than a threshold? What are we going to do with that kind of fraction of the data that we have? Or, we should also think about annotating the data, which is, again, something important. So, that when we were talking about those training approaches, supervised, unsupervised, self-supervised, I was saying that, some people went through the data and annotated that. Some radiologists did that, for example. So whenever your data needs some sort of annotation, there are a lot of questions that you should ask yourself. Who is going to annotate the data? What is the process or the procedure of annotation? Is that process reliable? Is that something that I can confidently report in my upcoming paper and say that, my model is based on this type of data annotation, or something that, reviewers could easily criticize and say that this is not reliable or valid, right? Then how much time are you going to spend on annotation? How much human resources do you have for that? How much money do you have to spend on that, right? What software are you going to use? So there are a lot of questions that come to mind when talking about annotation. Just have it in mind that annotation is a key piece of the data handling phase, and not to miss that when you're planning for the project. Now, I go back to the question that I guess one of the participants made earlier regarding how do we change images or any kind of input data when we are feeding them to the models. The answer is that these equations, these very, very big equations, deep learning models or so, they expect vectors and tensors as their input data. So vectors and tensors do have meaning in mathematics. I'm not going to go through the basics, but very simply, there are techniques for changing an image, the pixel values of that image, better to say, to a kind of a tensor, and then we can feed that tensor, each of the pixel values of that tensor, to a deep learning model. One very naive way of imagining that is that, for example, an RGB image has, 3 different tensors put upon each other. One of them is for the gray threshold, one for green, for green, for red, and for blue. And in each of these surfaces, we do have pixels, and each of those pixels have values. So one thing we can do is that we can say that the input of our equation is going to be all those pixel values that are here. And this was basically the idea for the simplest deep learning model or machine learning model, which was first built, right? Nowadays, we rely on more powerful techniques to find out what should be the input data to the models. But basically, you could easily say that all these pixel values or values of these tensors could be the input data to the model. Now, for text data, something similar happens, but with a different technique. For example, people can pick a kind of a dictionary saying that now I have a dictionary with almost all the words that are routinely used in the medical world. And then I can say that when the word "the" is seen in a sentence, the word is probably word number 4 in my dictionary. Then this cat might be word number 10 in my dictionary, on word number 2000. So basically you can say that I'm going to replace each of the words of this sentence with their index in my dictionary, and then feed that type of tensor against your data. Again, this is super, super simplified. There are a lot of techniques there. There are a lot of bottlenecks there that you need to address. And I'm sure that in workshops that we are going to talk about each of these modalities independently, I'm going to, either I or other people are going to talk about these techniques a little bit more. But just for you to understand, the input of these models are always numbers, and usually numbers in the format of vectors and tensors. So I stand here. Alex,
I hate to interrupt. I want to be mindful of people's time here. We're almost at the hour. So do you have any, closing thoughts?
One thing I can do is that I can very quickly go through the remaining slides and try to only mention what happens during the model development and other steps in 2 or 3 minutes, and then wrap up and wait for people who want to stay with us and ask questions. Is that good?
Okay. Yeah, and I think it's great that, the reason we're over time is because we've had a great discussion. So I'd rather have people's questions get answered, but still want to be mindful of that.
Yeah, of course, of course. So I'm going to very quickly review the remaining steps. So for model development, the very main question you need to ask yourself is that what algorithm are you using? Are you going to work with machine learning, deep learning? Are you already have any kind of pre-trained model to work with? By pre-trained, so let me jump very quickly here to this slide. So by pre-trained, I mean that you might have a very good working model for a problem, and now you are thinking of another problem that is not that much far away from your previous one. For example, you once trained a model to predict pneumonia, simple pneumonia, and now you want a new model for COVID-19. Probably these models are going to share a lot of weights from each other, right? Those parameters might be the same. So the fact that we do not start those weights randomly, but rather start from a previously working model is going to help us a lot. And that is what we call transfer learning. Now, another thing here to mention, I'm sure you all know, is that machine learning, deep learning is mostly based on Python language. It's a pretty much nice general purpose language. If you want to learn, don't forget Udemy. It has a very nice resources there, freely available from Mayo. Just go there. Model validation, not gonna spend too much time here. You all know that we need to have metrics. We need to have some sort of indices in order to go through and understand if our model is working nice or not. Then we need to compare our model's performance with, with a lot of kind of things, internal data, external data, to make sure it's generalizing enough. We already talked about the concept of generalization a little bit. Cross-validation data, I just ignore for now. Now, model deployment is something that happened for Alex's model and Tim's model when we talked about that earlier. So whenever you have a working model, you try to put it into real practice, really want patients to be seen by these models, patient data to be seen by these models. There are a lot of things to think about by then. You might have regulations, upper hand policies, ethical kind of issues, professional kind of issues, or even technical kind of considerations, like who is going to monitor these models? We have no guarantee that these models keep working as nicely as they were doing in the very first place, right? So we need to keep having an eye on them in order to understand the models are still working as we wanted them to work. So one of the things that people talk about recently is this kind of procedure for putting everything in a very nice workflow from the training to monitoring, and this is called machine learning operations. Again, feel free to go through that and Google that for yourself. Publication, as I believe it might be the final slides, is that you want to use your target journal, report that in a way that is reproducible, and try to stick to the standards that we have for publishing machine learning or deep learning papers as much as possible. Now, there are different standards existing there for publishing machine learning papers. One of them that I would like to mention, at least for medical imaging, is CLAIM. I'm going to talk about that more in the workshop that we talked about computer vision, but we do have other kind of standards coming up, for example, 3-pod AI or Probast AI, which might be a little bit more familiar for those of you who are more into statistics. So these are going to have some sort of equivalence for AI studies as well. And this brings me to my 2 final slides, which is actually some resources for you if you want to go through some further studies by yourself. So let me first start by this book by Eric Topol, Deep Medicine. This is a non-programming book. So if you want to learn something about machine learning, deep learning, like what we went through today, just go through this book. This would introduce the impact of machine learning to you. Likewise, this course on Coursera does the same thing, again, very non-technical. And we do have the Magician's Corner series on radiology AI published. This is a very, very valuable work by my mentor, Dr. Erickson, and this has a lot of working, this discusses the kind of general principles at the same time as letting you get your feet dirty and try to code something by yourself. So it's both coding and understanding the general concepts. And we do have some other things here as well. So we do have a very good machine learning, deep learning journal club every Monday at Mayo. So if you want to just join to that virtual meetings, this is something very nice to learn about some of the presentations. We do have a Master of Science program for AI at Mayo Clinic. Feel free to check the Mayo Graduate School website for that. We do have Mayo Clinic Cloud IT documentation for those of you who might want to work with Mayo Clinic, AI factory resources to train some models. And finally, I would like to finish by this, that Dr. Erickson and some of us in his lab are working on a very interesting book that hopefully would come up soon. And that is actually based on teaching medical deep learning for medical imaging to those of them who might be interested. So we are starting by going through the very basics of whatever machine learning concepts you need to know about, and then gradually making things more complicated and teaching you how to code in Python and specifically how to code deep learning and machine learning there. So look forward for further news of this resource when it comes up. And I guess that I need to wrap up everything by thanking a lot of people who helped with these slides and this presentation. From Dr. Kremes, Dr. Westendorf, Dr. Townsend, Dr. Erickson, and of course, Cody, Alex, and Barlia, as they helped me like always. So that was it. Sorry that I needed to talk very fast through these final slides. I hope that I could actually enlighten a little bit your minds about machine learning, and I'm here to answer your questions or hear your comments if you have any. And thank you, Alex, for all your help and assistance.
Yeah, for sure. Thank you so much, Puriya. An excellent, excellent job with your presentation. I think we covered a lot of material here and great feedback. So really encouraged by that. So one final note. So this is part 1 of the seminar series. The next one's going to be on March 5th, and it's yours truly talking about tabular data specifically. So clinical projects, things like that. So sounds like we're willing to stick around if people have questions. Otherwise, thank you so much for attending.